Hello everyone, so for today we're going to answer three physics problems in the University Physics book, and we're in chapter 14, which is all about periodic motion. So let's get started. So our first problem is all about energy in simple harmonic motion. So the problem is a small block is attached to an ideal spring and is moving in simple harmonic motion. It should be SHM on a horizontal frictionless surface. The amplitude of motion is 0.165 meters. The maximum speed of the block is 3.90 meters per second. So what is the maximum magnitude of the acceleration of the block? So here in our problem, we need to find the maximum magnitude of acceleration. So the given that we have is the length, which is x max is equal to 0.165 meters, while the v max is 3.90 meters. So first, if an object undergoes simple harmonic motion, Newton's second law will take its form. So we have a formula of f of x is equal to negative kx, and then we're just going to since we know that f is equal to ma, so we're going to use it ma x in order to get the to have an acceleration in the problem. And then for maximum, m is the mass of an object, and then a sub x is the acceleration, negative k is the spring constant, and x is the displacement. So for maximum displacement, we're going to wherein acceleration becomes maximum, we're just going to use equation 1, which is this one. So m a max is equal to negative kx max. So we're just going to rearrange the formula, the equation. So a max is equal to negative kx max over m. So since force is conservative in nature, the mechanical energy is conserved. Therefore, if the maximum displacement in the maximum displacement, energy is in the form of potential. Then at maximum speed, the Vmax energy is in form of kinetic. And both, take note that both energies are equal. So we're going to use this equation: 1/2 mv squared max is equal to 1/2 kx max, kx squared max. So we're just going to substitute the given. We still don't have the m, and we still don't have the k. So we're just going to divide this here, and then this one will be, since we're just going to divide it, and then it will be km is equal to 3.90 meters per second squared over the mass. So this one's our answer. This is our temporary answer. And then to solve for acceleration, we're just going to use the formula for acceleration that we got earlier. Then we got an answer of k over m is equal to this one. So we're just going to substitute it here. So since it's k over m, the value k over m is this one times x max. Since our x max earlier in the given 0.165, perform the indicated operations, and then we're going to have an answer of 92.2 meters per second. So that is the acceleration, maximum acceleration. Okay, for our next problem, which is all about the applications of simple harmonic motion. So we want to find the moment of inertia of a complicated machine part about an axis through its center of mass. You suspend it from a wire along this axis. The wire has a torsion constant of 0.490 Nm per rad. You twist the part of a small amount about this axis and let it go. Timing 128 oscillations in 270 seconds. So what is its moment of inertia? So in this problem, we need to focus on the moment of inertia. So we have a given okay, before the given, this is the free body diagram of the problem. So we are given a torsion constant of 0.490 Newton per meter rad and 128 oscillations in 270 seconds. So we need first to find the frequency. So frequency will be computed with the help of the oscillations given and the time given. So 128 oscillation over 270 seconds is equal to the frequency, which is 0.47 hertz. So the equation for frequency in angular simple harmonic motion, frequency is related to the moment of inertia and the torsion constant. So we have a formula of F is equal to 1 over 2 pi times square root of K over I. So K is the torsion constant, I is the inertia. So since we have a value for our frequency, and we need to find the moment of inertia, so we're just going to rearrange the equation with respect to the inertia. So the formula that we're going to use is I is equal to K over 4 pi squared F squared. So plug in the values that we have. K constant of 0.490 Nm per rad over 4 pi squared. The value of our frequency, which is 0.47 hertz squared. And then we're going to arrive at an answer of the moment of inertia, which is 0.056 kg per squared meter. So for our last problem, it is all about the symbol pendulum. So we all know what a pendulum is and what a pendulum looks like and how a pendulum works. So the problem is you pull a simple pendulum 0.255 meters long to the side through an angle of 3.5 degrees and release it. So first is how much time does it take the pendulum bob to reach its highest speed, and how much time does it take if the pendulum is released at an angle of 1.75 degrees instead of 3.5 degrees. So we are given a length of 0.255 meters and an angle 3.50 degrees, which is the release angle. So in order for us to get the first one in letter A, in a simple pendulum case, the formula is T is equal to 2 pi multiplied to the square root of L over G, wherein G is 9.8 meters per second squared. So we're just going to plug in the values, and then since we're looking for the time it takes to reach its highest speed, so T is equal to 1/4, which is equal to pi over 2 square root of L over G. Then we're going to plug in the value that we have, the length, which is 0.255 meters over G, and we're going to arrive at an answer of T is equal to 0.25 seconds. So in letter B, since the time is also being asked from equation 1, it is said that the period of a pendulum depends on its length. So no matter the angle is, as long as it has a same length as the given, the time it takes will just going to be the same. So since we need to bear in mind that the period of a pendulum depends on its length, so it is independent on the amplitude of the simple harmonic motion. Therefore, it will take the same time as letter A. That's all, and thank you.